All right, so today we're going to talk about inverse functions, and this is all going to lead up to eventually the idea of logarithms and exponential functions, and we kind of need this idea of an inverse function to drive the discussion for logarithms. So inverses, all inverses are, when we're talking about we're not even going to talk about functions first, we're going to talk about relations, is we're just going the opposite direction, okay? So I'm going to first put down, this idea of what we're going to call an inverse relation. And the reason we're saying relation is we want to kind of welcome things that not necessarily aren't functions. Okay, so I want to welcome maybe something that doesn't pass the vertical line test. I don't have to have it pass the vertical line test to be able to do this. So here's how we find inverse relations. So just put little stars. I have a couple things to say about inverse relations. So let's say a relation, again, it doesn't have to be a function. So like 1 could go to 2, but 1 could also go maybe to -3. And, I'm just kind of putting down some points that this relation, defines. So what does this relation do? It takes 1 to 2. It also takes 1 to -3. That's why I'm not calling it a function. It maps 4 to 5, and then it maps 0 to 7. This is an example of a relation, okay? So what an inverse relation does is it just goes the opposite way. So let's define that. So interchanging, okay, the first and second coordinates. I'm not going to say x and y because maybe we're dealing with s and t or t and s or something. So the first and second coordinates okay, in second coordinates of each ordered pair in a relation yeah, I'm not going to say that. Sometimes I realize when to say things and when not to say things. Doesn't always work. But what does that give us? That gives what we call the inverse relation. The inverse of that mapping, right? Or the inverse mapping. Okay, so that's one way that we can talk about an inverse relation. And then the other way that we can talk about this is if a relation is defined or is defined by an equation. So if a relation is defined by an equation, okay, then interchanging the variables then produces an equation of the inverse relation. So what an inverse relation does basically, and this will be a little bit easier to discuss maybe when we start talking about functions here, but what this basically does for us is it basically helps us go the other way. So for example, if I am given some relation, I'm going to call it little r for relation, and let's look at that one I just did, 1, 2, 1, -3, okay, 4, 5, and 0, 7, then simply enough, we're going to define a new relation, and this relation, how is it going to be related to r? It's going to be called the inverse. So the inverse relation, or the inverse of r, okay, is just going to be switching them. So I'm going to switch these. So now instead of 1 going to 2, 2 goes to 1, -3 goes to 1, okay, 5 goes to 4, and 7 goes to 0. So notice all my x's become y's and all my y's become x's. That is the definition of an inverse relation. Pure and simple, that's it. Okay. One other example, if we do have an equation. So if I do have an equation, let's see what's going to happen with that. So for example, let's consider the circle, because the circle isn't a function, right? So we can call that a relation. So let's consider the circle x minus 4 quantity squared plus y plus 2 quantity squared equals 9. So look at the circle. There are some things we know about the circle, right? The center is 4, -2, and the radius is 3. If I consider the inverse of this circle, so the inverse relation, remember what that last definition said is if my relation is given by an equation, then to find the inverse relation, literally all we do is switch the x and y. So everywhere I see an x, I'm going to put a y, okay? And everywhere I see a y, I'm going to put an x. So again, what does this mean? This means for every point on this circle right here, the inverse relation, all the points on the inverse relation will just be these points right here, but switched, right? Interchanging the first and the second coordinate. And look at, you can kind of see that because if we look at what the center of this circle is, well, what about this x coordinate? The center is -2. And what is this y coordinate? It's 4. Now the center is not on the circle, but my r is still 3, okay? So if I were to graph this, oh no, this could be bad. I actually, let me be smart here. So, sometimes I am, sometimes I'm not. So I'm going to bring in my graph right here. So let's see, I have, let me write this down here so I can see actually what I'm doing. That would be great. So I have the first circle, right, or my first relation is 4, -2, and then I have -2, 4 is the center of the other circle, my inverse circle basically. And I want to see how the graphs of these maybe kind of match up a little bit, right? So let me get rid of some of this stuff right here and let's graph some of these. So I'm going to graph this first one in purple, maybe. 4, -2, so I'm going to go over 4 and down 2, and then I have a radius of 3. 1, 2, 3 here, 1, 2, 3, down 3. Okay, so remember, this is a lesson in imagination. I'm going to draw a circle. I amuse myself quite greatly with attempting to draw a circle. Pretend that's a circle, people. Pretend, pretend, pretend. Okay, now I want to graph. Let me get a different color here. Okay, I want to graph now this guy right here. Okay, so I'm going to go -2, and then I'm going to go up 4. 1, 2, 3, 4. Okay, and I'm going to go to the right 3, 3, still 3. 1, 2, 3. 1, 2, 3. 1, 2, 3, okay? And notice I get this lovely circle right here. Pretend it's a circle. Pretend it's a circle. So something that's pretty cool about graphs of inverse functions is that if you look at the line, or graphs, inverse relations, I shouldn't be saying functions. Let's look at this line y equals x right here. I'm just going to kind of make it a dotted line. One really unique, not unique, but kind of cool thing about graphs of inverse relations and functions as well, we're going to see, is that they're actually going to be reflections about the y equals x line. If you kind of think about that, if I have any point, like if I had this point right here, and let's say this point, which is 8, 2, is on my relation, then if I'm going to go and switch these, I would get 2, 8, correct? For getting a point on my inverse. And if you notice, what we've done is we've just basically reflected it across the y equals x line. And that's going to be true for all inverse relations and all inverse functions. Because we're just switching x and y, it's just going to be a reflection about that line. So it's actually a pretty cool thing. If you look at the graphs of these functions, or relations, sorry, then they're just going to be reflection. Notice my purple circle here, if I flipped it over this y equals x line, I would lie right on top of the blue circle right there. So kind of a cool thing about relations. One other example that I kind of want to talk about. Let's get rid of those circles here. Oh, that's kind of cool. Clear that. Let's talk about, for example, let's say I have a cost. The cost of producing X units of some good, right? X units is given by C of X equals 400X plus 200. So a quick example, let's see what this means for the inverse. Okay, so another way to describe this is y equals 400x plus 200, where in this case, think about what your input. So my input in this case are units produced, right? And then my output, I teach business calculus, so this is always fun to do these examples. My output is going to be the cost to produce those units, okay? So my input is units produced, my output is cost. So if I wanted the inverse, again, what I'm going to do is I'm just going to switch x and y. So I would get x equals 400y plus 200. And if I wanted to do, I could solve for y to make this kind of look, remember, this is my inverse right here. This is it. This is my inverse. And now think about, okay, so now as if I rewrite this, I'm going to get, if I solve this, I get y equals x minus 200 over 400. And you could simplify that if you wanted to. But now, remember, my input and my outputs have switched. So now that I have this function, now that I've rewritten it in kind of a form I'm more used to, what is my input going to represent? That's going to be the cost, right? And what is my output going to be? My units produced. Why would this be beneficial maybe to have an inverse function of something like this? Well, what if I know I have a budget of $10,000, right, to produce whatever I'm making, like Math is Fun t-shirts, right? Because we all want Math is Fun t-shirts. It'll be high demand for Math is Fun t-shirts. Let's say I want to know, right? I want to put in the amount that I am going to spend, and what this guy then is going to spit out for me are the actual units produced. So a lot of times inverse functions help us kind of see something in a different way, or help us get maybe to a new way to find what we're looking for. So again, in this case now I have my input is cost, my output is units produced. So if I know I have $10,000 to spend, then I know how many units I'll be able to produce, right? So that's kind of a good example of why maybe we care about this idea of inverse functions and kind of, I don't know, you could call it maybe real life. Right. So, all right. So, couple things. So we've been talking about this relation. What we want to really look at now is if I'm given a relation, or if I'm given maybe a function and I want to find its inverse, how will I know if the inverse is also going to be a function? So for example, given, let's say some function f, and let's say that f takes 1 to 2, 3 to 4, -1 to 5, and I don't know, 0 to 4. Okay, notice this is a function because for every x value you have one and only one y value, right? So I don't have any x values repeated like I did in that last one. Is the inverse a function? Is the inverse of f a function? So when I have something like this and I'm just basically given the points, what I can say, I can look at, okay, well, here's my inverse. My inverse, I'm just going to switch these points. I'm going to have 2 goes to 1, 4 goes to 3, right? 5 goes to -1, and then 4 goes to 0. Well, if you look at this, what this new mapping is, notice that if I ask you what does 4 map to, 4 maps to 3, but 4 also maps to 0, right? So that's a problem. It's not a problem. It's just that this means that my inverse is not a function. So this guy right here, not a function. And in mathematics, we really like to work with functions. We want to know that for every input, there's one and only one output. So likewise, when I'm dealing with a function, I want to know if when I take its inverse, meaning when I switch that x and y, I want to know, is the resulting thing going to be a function, right? And one way we can do that is we can test to see if a function is what we call one-to-one. In this case, why did this happen, right? Why did I get a point where I was not going to have a function? Well, notice I have a repeated y value. Over here, for this guy, that doesn't make it not a function, right? Doesn't make it not a function because every x value goes to one y value. The problem is when we're switching these, right, what I've done is I've switched all these y values to be x values, and now I'm not a function. So what we're going to look for is we're going to look for functions that are what we call one-to-one, which means for every x value, there's only one y value, and there are no two x values that share the same y value. Now, I'm going to write down the definition for one-to-one. You know, I've had my students in the past spend time, oh, sorry about that, actually showing it, proving that something is one-to-one algebraically. I'm not going to have you do that because I'd rather you spend time on like finding inverses, determining domains, stuff like that. But it is very important that we put down what a one-to-one function is, okay? And we can kind of talk about how to easily think about how to determine if something is one-to-one. So a function f is what we call one-to-one. And the way I think about this is every x and y match up and they don't share anything. That's not a mathematical definition of it, but that's kind of how I think of this. Is one-to-one if different inputs, meaning if I take two x values that are different, right? If I'm not hanging out with the same x value. So if different inputs have different outputs. So if I take two x's that are not the same, then they go to different, oh, I can't spell. They go to different y values. Okay, so i.e., or that is, I guess your book uses that is. That is, how do we say that? So different inputs means different outputs. I'm going to show you the definition of this. I'm not going to have you actually show that something is one-to-one. I mean, it's an interesting practice, but we don't really need to do that. That is, if A is not equal to B, then f of A is not equal to f of b, okay? So again, all that's saying is if I take two x values that are not the same, then when I evaluate the function at those x values, okay, their y values are not equal. So let me show you why this relation right here didn't work, right, for being one-to-one. Here, if, whoops, got a little too excited there. Here, if I look at 3, right, and then I look at this x value here, 0, those x values are not the same, and yet when I take f of 3, right, I get 4, and when I take f of 0, I also get 4. So this is an example of a function that is not one-to-one because I have two x values that shares a y value. Again, why is that a problem? Because when I switch my x and y's, right, we're going to not have a function then. Okay, so that's pretty much it. There's another way that you can say that is, you know, if my two y values, if I have two y values of the same thing, then I'm at the same x value. So that's all I'm going to really say about that. But let's talk about inverse functions. Oh, I'm sorry. And let's write down some important stuff about inverse functions. Okay. The other thing about one-to-one that we should put here is it actually passes what we call the horizontal line test. So as opposed to the vertical line test, kind of forgot about this. This is a great little test. It actually passes the horizontal line test. So that means I don't have any, so if you think about, you know, a function that is not one-to-one and a classic one is x squared. If you look at a horizontal line here, do you see how these two x values right here share the same y value? It's still a function, but it's not one-to-one. So we say that that x squared does not have an inverse that's a function. How do we get around that though? Because a lot of times mathematicians are like, yeah, but I really want to talk about the inverse of x squared. What we do is we restrict the domain and we say, well, let's just consider x squared as long as x is greater than 0. And then I can find an inverse of it because I've restricted that domain and I'm one-to-one on that, just that half of x squared. Okay, so a couple things about inverse functions. If f is one-to-one, so the easy way of saying that is one-to-one, then its inverse. So let's introduce some new, oh man, I cannot spell inverse. introduce some new notation here. Here's what the inverse is going to be, f to the negative 1. Please realize that that is not an exponent. I know that's weird, but f isn't a variable, right? F represents a function and it's function notation. So what this means is this is the inverse function of f. It does not mean 1 over f, okay? Again, this means it's the inverse of f. It does not mean 1 over f. It is not an exponent, okay? If f is 1 to 1, then its inverse, this new function, which we'll call f to the negative 1, is also a function, or is a function, okay? All right, I'm going to write a couple more things here that I haven't actually talked to you about, but let me write them down and then I'll kind of tell you why this is true. So let's assume f is 1 to 1 and then its inverse is a function, okay? If that is true, then the domain of f is equal to the range, and I'm going to show you this in a minute, so write it down and believe me, okay, of its inverse, okay? Likewise, the domain of the inverse is equal to the range of the function. And this, I hope, well, I'll show you kind of a picture, but I hope this kind of makes sense because remember, we're just switching x and y values. So remember, all of the x's for f are all of the y's for f inverse, right? Because we switch them. So that makes sense here. And then remember, the x's then of f inverse are really all just the y's of f. I don't know if anything I said there made sense, but good. The other thing about inverse functions that's kind of an interesting thing that we will see later on is that when we compose inverse functions, so we've talked about composition before, and I'll talk about this in a minute, basically what they do is they undo each other. Okay, remember, we're going one way and then we're going the other, and if we compose these, oh, that shouldn't be f, excuse me, how embarrassing. That should be x. So if I apply, f inverse and then I apply f, we're going to end up where we started. And if I apply f and then f inverse, we're going to end up where we started. So this right here is basically all the stuff about inverses, and now we're just going to do a bunch of examples. Okay, but I want to show you one other thing about this and about the last couple. Man, Sarah. About the last couple claims that I made. So one way that you can think of what these inverses do. So let's say we're in some domain, right? And what does f do? F takes an x value, right? And it spits it out into its range. So this here, over here, I'm going to say d sub f for the domain of f, and then it spits out its y values in its range. So remember, what does an inverse function do though? An inverse function, we're going to switch that order. So what an inverse function does then is it's going to go the opposite direction. So this stuff over here will be the domain of f inverse, and then it's going to spit out stuff here, which will be the range. So if you notice, the domain of f then is equal to the range of the inverse, and here the domain of the inverse is equal to the range of f. I hope that kind of makes sense. The composition part, so like if I have an x value here, and let's say I apply f to it first, right? And so it's going to spit out some y value. So let's say this is f of x. But then remember, if I bring my composition, then if I apply f inverse to it, it's just going to come back to that x value, because that's exactly what f inverse does, is it just switches the order of that. So this guy right here would be f inverse composed with f, because f goes first. And as you can see, we just end up where we started. Likewise, if I started over here with some x value and I applied f inverse, right, I would have f inverse of x. And then I bring my f and I apply my f, right? Notice again, we're back at x. So this yellow right here tells me then that if I do f composed with f inverse, meaning f inverse goes first, we're just going to get x. That picture right there looks a bit confusing, but I hope it kind of makes sense. All right, you guys, now what I want to do is I just want to do a bunch of examples for you. Oh, there was one other thing that I wanted to add to this right here. Sorry about that. Ooh, sorry. Oh man. And we already talked about this. I just want to add it kind of to all of your to your notes, but let's add one other thing right here. And that is that, what does this mean about the graphs of these functions, right? The graph of f inverse is the graph of f reflected about the line y equals x. Ooh, reflected about y equals x. Whoops, sorry about that. All right, you guys, so we're already at 25 minutes, so let's get some examples going, and then let's call it good. So we're going to kind of do, I am so sorry about that today. I don't know what my problem is. Don't answer what my problem is. We're going to do just a bunch of examples here, okay? And we're going to do all the stuff to the examples, okay? So couple ways. Oh, so first of all, let's talk about how we've, well, before we even get there, actually, let's verify using composition okay, verify using composition that, and what I'm going to do is I'm going to use like a little bit different notation. I want to verify that, let's say f is 3x plus 6 and g, which I'm going to call 1/3 x minus 2. Let's verify that they are inverses. So I'm going to use this fact that I know composition, right? When I compose these two, sorry, geez. When I compose these two functions, I'm just going to get back out where I was. So basically, all of these things are true. If f is 1 to 1, then all of these things basically tell me that I have an inverse. So one way I can do that is I can show composition. Got to show it both ways, okay? So it doesn't matter with which way I start. Ooh, that sounded fancy. So I'm going to do f composed with g. That means I'm taking f of g of x. So that means everywhere I see an x in f, I am actually going to put the function g. So notice I just replaced this x right here with this entire function. And again, if these are inverse functions, I should just get x back out because I'm putting in x and I should get x back out. Let's take this 3 through. So 3 times 1/3 is just 1. I get minus 6. Oh, I love doing these. Plus 6. Sure enough, look at what I get. I get x. Yay. Got it. That's a smiley face. That's smiley face worthy. Let's do g composed with f really quick of x. So this is g of f of x. Okay. So so I have to show both ways. When you're going to show that something, verify that they're inverses using composition, we need to show that both ways it works. Oh, sorry about that. So I'm going to take this 1/3 through. That gives me x. 1/3 of 6 is 2. Minus 2. Look at that. Isn't that great? So those guys are gone. Lovely. So sure enough, we need a smiley face with that too. We have verified that these two are indeed inverses of each other. We're going to do some more verifying of that. Before we get there, let's talk about how to find an inverse. So that was a good time. Right? We've actually already found an inverse. We did that with the cost function. So let's kind of write down some steps of what it means to find inverses, and then we'll do a couple and then we'll call it good, okay? Because I'm almost at 30 minutes. So, all right, so first step, you want to rewrite or replace. So if you're given an f of x, we want to replace f of x with y. And remember, we kind of did that with the cost function, right? We said c of x was y. Then this step right here is the most important step because this step number 2 actually gives you what the inverse is. This is the inverse. Inverse. This is the inverse right here in 2. Once you switch x and y, that is the definition of what an inverse is, and that gives you your inverse. However, we're not used to graphing and we're not used to seeing functions where y is the dependent variable or independent variable and x is the dependent variable. So what we do there is we're going to now manipulate this equation that we got in 2 to get it to look better, okay? To get it to look like something that we are used to dealing with, which means y is the dependent variable and x is the independent variable, okay? Remember, 2 and 3, you're working with exactly the same equation. You haven't changed anything at all. And then finally, number 4, we're going to replace y. And I want to see you do this. I want you to replace y with f inverse of x. Oh. Oh, sorry about that. I just sneezed. So, for example, let's look at that last example we did. Find the inverse of f of x equals 3x plus 6. Okay, this will be a pretty simple one, but I want to verify that we get out that g of x. Okay, so find the inverse of 3x plus 6. We did this with the cost function, but what my first step, right, is to rewrite f with a y, because I know my inverse switches x and y, so let's get some y's in there. Second step, interchange x and y. So everywhere I see an x, I'm going to put a y. Everywhere I see a y, I'm going to put an x. By the way, this guy right here is a line, right? 3x plus 6. So I just want to kind of in the back of my mind say, okay, this is a line. So I know that it's going to pass the horizontal line test, which means I know it's 1-to-1. Sorry about that. I know it's 1-to-1. And I can find a function that, or its inverse that is a function. Okay, switch x and y. Again, we're not used to really graphing something that looks like this, so I'm going to go ahead and now solve for y. So step 3, solve for y. So I'm going to subtract that 6. That equals 3y. I'm going to divide everything by 3. And so 4, replace y with f inverse. That's gone. So what is f inverse of x then? X over 3, or I could write that as 1/3 x minus 2. Look at that. That's exactly what we had in that other problem. If I wanted to graph these, I could do that. So if I wanted to graph these, the first one was 3x plus 6, so I'm going to go up to 6. Oh, Sarah, my goodness, go up to 6. I'm going to go up 3 over 1, or I'm going to go down 3 to the left 1. Down 3 to the left 1. Right, so I get this line, pretend it's a line, right here, darn it. And then let's do 1/3 minus 2. I'm going to go down 2, I'm going to go up 1 over 3, up 1 over 3, or down 1 to the left 3. I think that purple line right there should go, so, oh darn it, let's not do that. Sorry, I should be graphing on that, but that's okay. So if I graph this guy, oh man, Sarah, knock it off. If I graph this guy, if you notice, sure enough, I didn't do a great job of that, but they are reflections about the line. It should be anyway, y equals x. Okay, so if you look, you can see that they are reflections about that line. Just gonna clear that all out. Oh, I didn't mean to do that. Okay, anyway, you get the picture. All right, so that's how we're going to find inverse functions. And if we talk about domains and ranges too, let's do one example with the domain and range, and then I'll call it good because we're already at 32 minutes. Maybe we'll do 2 examples, okay? Seriously, people, I bet you're so sick of me doing that. I'm sick of myself doing that. Let's look at another example. So I want you to find the inverse. And so we'll just find the inverse, state the domain and range, domains and ranges of f inverse, and use composition to verify. So this is all of it. To verify that they're inverses of each other. Okay, so let's look at f of x. So I want to look at one here. We're going to absolutely get a fraction because we care about fractions, and fractions are just interesting to deal with. But what if we had like f of x equals x cubed plus 3? No. I don't want to do 3, I lied. Let's do x cubed plus 4, okay? So again, let's find the inverse. So the first step, rewrite the f of x with a y, x cubed plus 4. This one should be pretty straightforward. Let's switch x and y. Remember that one, that right there, that gives me my inverse function right there. Again, remember this is x cubed, so it's shifted up 4, passes the horizontal line test, so it is 1 to 1. Now I'm going to have to cube root both sides, but before I can do that, to solve for y, I have to do x minus 4 equals y cubed. And now finally I'm going to cube root it. So what is my inverse function? My inverse then, cube root both sides, is the cube root of x minus 4. Okay, so there's my inverse function, which is what it asked for. Now it wants the domain and range. So remember, you guys, the domain of f is equal to the range of f inverse, and the domain of f inverse is equal to the range of f. We are really good at finding domains, right? We're good at determining what x values are invited, what x values are not invited. So what you want to do is you just want to find the domains and then set those equal to the inverses. So those are actually pretty simple to do if you can think about what the domains of your functions are, as opposed to if you think about the ranges. These are all pretty easy because the domain of f is all real numbers, right? The domain of f inverse, I can take the cube root of any number I want, all real numbers. So that means then the range of f inverse, because the domain is all real numbers, the range of f inverse is all real numbers. And likewise, the range of f then, because the domain of f inverse is all real numbers, the range of f is all real numbers. So that's pretty easy. And then using composition to verify, so let's take f composed with f inverse of x. Here's my f, right? Let's plug in f inverse. So I would get, instead of x cubed, I'm going to get the cube root of x cubed minus 4 cubed, all plus 4. Okay, the cubed and the cube root cancel out. Yeah, I see it. That guy shouldn't be there. I was wondering why I wasn't going to get the right answer. I end up getting x minus 4 plus 4. Those guys cancel, and we just get x. Likewise, f inverse, composed with f of x. Okay, everywhere I see I'm going to have the cube root. This x right here is going to be replaced with x cubed plus 4. And then I have that minus 4. Please be careful here when you do this. You may not cancel these cubes right here. You can't do it because you're working inside the cube root. So these 4's cancel first. Then I'm left with the cube root of x cubed. What is the cube root of x cubed? That is x, and we're good to go. Okay. All right, you guys, I wanted to get done in 40 minutes. I think I can finish this last problem in 3 minutes probably. So I want to do one with some fractions. So let's look at, so this will be part B. I want to do all of the same stuff. Okay. So let's look at f of x. Let's do something kind of interesting here. X plus 1 all over, let's say, 2x minus 3. Okay, this one's going to be a little bit tricky, but we can do it. So I'm going to set y equal to x plus 1 all over 2x minus 3. Okay, now I'm going to switch my x and y values. That is going to give me my inverse function. Now this is where these can get a little bit tricky when we're dealing with these fractions. Problem is I want to solve for y, and the issue here is I want to solve for y, but notice I have two terms with y in it and I have a fraction. So the first thing you're going to do is you're going to get rid of this fraction. It's easy to do when we're dealing with an equation, right? Because what I do to one side, I'm just going to do to the other. So first step with that is I'm going to rewrite it without the fraction. Okay, now look at what I have left. Remember, I want to solve for y. So my goal is going to be to get every term with a y by itself. But before I can do that, I have to get rid of this multiplication right here. So I'm going to take my x through. I'm going to get 2xy minus 3x equals y plus 1. The whole reason I did that was to free that y from the evil x. And now notice I have two terms with a y in it. So I'm going to get every term with a y on one side, every term without a y on the other. So I'm going to bring this y over. That gives me a minus y. And then I'm going to take that 3x, I'm going to add that over to this side. So I get 3x plus 1 over here. Now, Notice, what do I have common to these two terms? I have a y common to these two terms. So I'm going to be, if I factor that y out, I'm left with y times, don't forget y divided by y is 1. I get 3x plus 1 over here. And then finally, all I have to do is divide both sides by that 2x minus 1. So what is f inverse? It's going to be 3x plus 1 all over 2x minus 1. Whew, that was a good time. There's my f inverse, there's my f of x. Let's do domain and range, and then I'll let you verify these are inverses with composition. This one is a little intense, but we did composition like this in section 2.3. Also, look at the fun sheet solutions online. You'll see that I do several examples with composition. If you have questions and you want me to record how to do those compositions, just please send me a little note, and I'd be happy to do that for you. So let's look at domain really quick, and then we'll call this lecture. We'll put it to bed. So let me get rid of all this stuff here. So domain and range. Let's start with domain. Okay. So the domain of f. I'm going to keep this simple, and I'm going to use set notation. If I set the denominator equal to 0, I see the domain of f is all x as long as x is not 3/2. Okay. And then the domain of f inverse are also all x's as long as x is not equal to, well, if I solve that, I get 1/2. Okay, so the range of f inverse then is just going to be whatever f leaves out is what the range is going to leave out for f inverse, except remember, range are y values, so I'm going to have the same numbers except I'm going to do y values. You are also welcome to use interval notation, and then you don't actually have to worry about x or y's because your interval notation automatically takes that. Likewise, my range for f, now I can find the range for f, is going to leave out whatever my inverse, the domain of my inverse, oh, I didn't put y, whatever my inverse is. So what is y going to leave out? Y is going to leave out 1/2. So notice how these guys are kind of the same, not kind of, they are, and these guys are the same. We just have the x and y's. Whew, 41 minutes. I got to stop talking. If you guys have questions about how to compose those, please let me know. Send me a quick note. I'd be happy to record another quick lecture about how to compose those two functions. All right, thanks, guys.